In this section, we're going to learn about vector-valued functions. So let's start off with the obvious question. What is a vector-valued function? So it's what it sounds like. It's a function where the output value is a vector. So a vector-valued function R has the form like this. Okay? Okay, so what does that mean? So if you haven't seen this notation before, it means function R has this as its domain and this as its codomain. Basically, these are what we can plug into R, into the function. This is what function R spits out. That's the output of the function. Notice it's taking in a scalar value, a single numerical value, and the output is a vector. Now here, n could be any number. 2 or 3 is what we will be dealing with in this class, right? 2-dimensional space, 3-dimensional space. Okay, so what does this look like? This means so if R maps, function R maps something in the real numbers to, say, 2-dimensional space, then what we might write is R of t equals a vector that's dependent on two functions that we're more used to, okay? F of t, g of t, okay? It takes in a single value t, and the output is a vector, where both components of the vector depend on the input value t. Okay? This is written in component form. I could also write it in terms of the standard unit vectors, I and j. Okay? And similarly in 3 dimensions. If that n is equal to 3, then it's the same thing. We just have 3 components. Okay? Input is a single value. The output is a vector where each component of that vector is dependent on the input variable t. And again, I could write it either in component form or in terms of the standard unit vectors. Okay. So what does it look like in practice? Let's give you an example. Okay. Consider the function R of t equals cosine of t sine of t. Okay, so for each value of t, we plug in the value of t, and the output is a vector where the first component of that vector is cosine of the t we plug in. The second component of the vector is sine of the t we plugged in. So just as a brief example, so let's do r of pi over 2. The output of this will be a vector with components cosine of pi over 2, comma sine of pi over 2. And that's easy enough to evaluate. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Okay? By combining all possible points, all possible outputs for all possible inputs t. Okay? If you look at all the different t's we could plug in, you'll get a bunch of different vectors popping out, right? If you take the points that those vectors point to while in standard position, you get a curve. In this case, a 2-dimensional curve. Let's see what this particular curve looks like. I have an example ready to go. Okay. In this particular example, here we have the vector valued function cosine t comma sine of t displayed, and we get a circle. Now, if you think about it, that shouldn't be surprising. Cosine of t is the x value of the unit circle for a given angle, right? For angle t. Sine of t is the y value of the unit circle at angle t. That's just the definition of sine and cosine. Okay, we have this here. We have our unit circle. This point here is the point xy. That's that x and that y. Okay, by definition, this is angle t. Then by definition, cosine of t equals the x for a unit circle. Sine of t equals 1 for or y for a unit circle. Okay, or if you prefer, x over the hypotenuse of 1, y over the hypotenuse of 1. Okay, so we shouldn't be surprised that when we put all this together, we get a unit circle. Okay, now how does the t work? The t is a parameter. Notice it's not reflected per se in the circle. The only points we're graphing here are points involving the x and y outputs. So how does the input work? We can think about the input as a time variable. Instead of just having a static path or a static shape, we can think about us traversing the shape. Okay, so if I add a point here, if I let the input variable, the t, change, we traverse the path. In this case, we traverse the circle. Okay, so the curve itself is the path the points traverse as t increases. Okay, this is a particularly important example. We see this a lot whenever we want to talk about something circular. It involves cosines and sines like this. This is the formula for a unit circle expressed in parametric form, expressed as a vector valued function. All right, what happens if we want a circle of greater radius? Well, if I add 3 to both sine and cosine in front here, I get a circle of radius 3 instead of a circle of radius 1. Okay. And I could even change the values if I have two different values. Say I keep cosine at, let's make cosine 5 and keeps this coefficient in front of sine at 3. Look what I have now. It's an ellipse. And that kind of makes sense, right? Because when cosine is biggest, that is when the angle is pointing along the x-axis, when the t value, if you think of t as the angle, if it's pointing along the x-axis, then I maximize the value of this. I get 5, right? It's bigger. But if I maximize the value of sine so that t, the angle t is pointing at the y-axis going up or down, then it only goes 3 up or down. Okay, so we go 3 up and down, 5 left and right. Okay. Now, interesting thing about parametric curves like this, vector value functions like this one, the curve may be the same for different parametric functions. There are different ways that we can traverse a curve, right? So let's go back to the unit circle example. What happens if I, say, change the sign on one of these? What if I go negative cosine? Okay. Notice I still have a circle. Let me hide the point for a moment. Notice I still have a circle, right? Let's add in the point. So I traverse the same curve, but notice now I'm traversing it counterclockwise. Whereas before, when I had positive cosine, I traversed the curve clockwise. So depending on how I parameterize the curve, that's a way to say, depending on how I find a vector valued function to traverse the curve, I could either traverse it clockwise, like this. I'm sorry, counterclockwise, like that. Or if I throw a negative in front of, say, the cosine, I could traverse it counter or clockwise. Sorry, I'm getting hung up on the fact that the natural direction of rotation in math is counterclockwise. So this direction here, it's a little odd, but traverses the curve, right? So there are different ways to traverse the curve. I could also traverse it at different speeds. Okay. Nope. So now that t is going twice as fast. Okay. Now what happens when I go? Notice that it's going faster now. Okay. It's going twice as fast as it was before. So the output could give me a space curve, but the way the curve is parameterized, I could either be going around the curve slower or faster or counterclockwise or clockwise. Okay, there are lots of ways to traverse the same curve. All right, let's look at another example. Find a vector valued function with a curve the same as y equals x squared. Okay. Now, as we've seen, there are generally lots of ways to construct a vector valued function to traverse a specific curve. You can go forward, you can go backwards, you can go slow, you can go fast. Okay. But if all we need is one example, then an easy case in this case would be to, since we know that y is always equal to x squared, let's let t be equal to x. Okay, what would that mean for y? Well, if x and t are equal, then y would be equal to t squared. Okay, so this is a vector valued function that will traverse the path of the parabola y equals x squared. Okay, there it is. And if we can watch the point traverse the path, and we do indeed traverse the parabola. Okay. There are other examples I want to show you. What if we want let's consider this one. Cosine of t, sine of t, t. So now this is in three-dimensional space. Okay, so this is going to be a three-dimensional curve in space. What's going to happen here? Well, if we look at just the x and y, if we focus on just those, that looks familiar. We already know what's going to happen there, right? That is the parameterization for a circle. We're familiar with that. Okay, so if we're just looking down the z-axis, we're going to see a circle. What's the z doing? The z is doing something different. It's just equal to t. So as t increases, the z value will increase. So what we're going to get is we're going to get, in the xy plane, we go around a circle, but then the z increases. So we're going to corkscrew up. Okay? Let me show you. Okay? So there's our corkscrew. But look, if we look at just the xy plane, we get a circle. And if we focus on just that plane, we see that we go around the circle. Okay? But with that extra component, that extra z value of t, not only do we just go around the circle, we also go up, right? As t increases, the z value of the output increases. So we have this corkscrew behavior. Okay, I wanted to give you just a couple other examples. This is one we're already familiar with. We've actually already dealt with vector valued functions. We just didn't call it that at the time. We've learned how to parameterize the equations of lines in any number of dimensions. So this is the equation of a line in 3 dimensions. It goes through this point, and it's going in this direction. Okay, we learned that a few sections ago. So it's just a vector valued function, right? We are plugging in one variable. It is outputting a vector. If we look at the point at the end of that vector and trace all the possible points, we get a line. So here we see that orange point traverse the path of the line, traverse the path of the space curve. Okay? And I wanted to give you one more exotic example. This one's quite complicated. This isn't one to memorize. It's called a trefoil or trefoil. I'm not really sure how it's pronounced actually. But it's pretty complicated, right? Quite pretty though. So you could do all kinds of fun things like this with space curves. Let me display the point here. And you could see that it can model motion. And that's one of the very useful things about this. Sometimes we will use these vector valued functions only to describe a space curve. Sometimes that's all we care about. Other times we do want to use it to describe the motion of a particle, for example. Either way, these are very, very useful. This is a very, very useful tool, these vector valued functions, to describe this kind of behavior. So how do domains work for these vector valued functions? Let's take a look at an example to give us an idea. So here we want to find the domain of this vector valued function. Remember, the domain are all the values of the input you're allowed to plug in. When a domain isn't explicitly given, then you have an implied domain. It's all the values you can plug in that don't break something, basically. Okay? And that's what we're looking for here. We want to know all the possible t values that won't break something. Now, for a vector valued function like this, in order for t to be in the domain, it has to be in the domain of each individual component, right? If any one of the components doesn't work, then we don't have a vector anymore. So only the t values that are in the domain of each component are in the domain of the vector valued function in total, okay? So our strategy here is to find the domain of each component and then find the intersection of all those domains. That will be our total domain for the entire vector valued function, okay? So let's look at component 1 here, root 3 minus t. Okay, so this is the x component. What would be the domain of 3 minus t? What t's would we be allowed to plug in? So for square root, the thing we know is we cannot plug in a negative number. So that means that the input, 3 minus t, must be greater than or equal to 0. 0 is okay. We can take the square root of 0. Anything positive, no problem. It's just negative numbers that are a problem. Okay? So 3 minus t is greater than or equal to 0, which means if I move t to the other side, 3 has to be greater than or equal to t, or if you're like me and prefer t on the left side, flip the inequality around, t has to be less than or equal to 3. So the only t's that'll work for this first component are the t's that are less than or equal to 3. Okay, so that component's done. So we know that for this vector valued function, At the very least, we can't have t's any bigger than 3. 3 is the absolute biggest they can go. Okay, let's look at the y component. So that's 1 over t squared plus 1. Okay, so what do we have to worry about here? We don't have any square roots, no funky functions. What we have to think about here is getting a 0 in the denominator, right? That's one of the big ones, right? We cannot have 0 in the denominator. So I need to make sure t squared plus 1 isn't 0. So to make sure it isn't 0, I'm going to see where the denominator is 0 and then exclude that from the domain. So I'm going to set t squared plus 1 equal to 0 and be very clear, this is what we don't want. Okay, I do not want t squared plus 1 equal to 0. So if I find any t's that make this happen, they are automatically also excluded from my domain. I cannot have a 0 in the denominator. All right, so t squared plus 1 equals 0. I can solve for the t squared. T squared equals -1. I could take the square root, unsquare the t. So t equals plus or minus the square root of -1. What's a square root of -1? It's an imaginary number, right? And in this class, we're not dealing with imaginary inputs or outputs. So this is not a real solution. There are no values of t that will make the denominator 0. And if actually we take a moment and think about it, that makes sense. Our denominator is t squared plus 1. T squared is always non-negative, right? The smallest it could possibly be is 0. If I plug in anything else, because it's squared, it will become positive. And then on top of that, I add one more. So this will always be a positive number. 1's actually the smallest it could ever be. So I cannot make it 0. Okay? So there's no new restrictions from my y component. The y component is, the domain is all real numbers. Okay, for just that component. One more component to go, the z component. So the z component is natural log of t plus 4. Natural log, that's a little bit of a tricky one, right? We have to jog our memory for that one. Natural log is one of those special functions with a special domain. The rule is we are only allowed to plug in positive values into a natural log. If you remember the graph of a natural log function, looks something like this. Come on. There we go. Okay, we have an asymptote on the y-axis. And then it looks kind of like this. All right? So any positive number I'm plugging in over here, any positive number I can plug in, no problem. But I never quite get to 0, right? It goes down, 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 keeps on getting closer to that asymptote, but it never quite reaches it. So the only values you're allowed to plug into a natural log function are values that are strictly greater than 0. Okay, not greater than or equal to, strictly greater than 0. You're not allowed to plug in 0. Let's isolate the t, subtract the 4. That means t needs to be bigger than -4. Okay, so if we put all those components together, the restrictions from all those components together, then the first component, I cannot have t any bigger than 3. 3 is the absolute largest it could be. There are no restrictions on the second component, but on the third component, I also need t to be bigger than -4. So to make sure all of these components work at the same time, I need to make sure all of these restrictions hold at the same time. So in this particular case, my domain would be the set of all t's such that t is between -4 and +3. Okay, that makes sure that both this happens and this happens. And so that would be the domain for this vector valued function, that would make sure each of the components always works for all the t's that I plug in. Let's get a little bit of experience plotting these vector valued functions. Now, there are different ways we could do it. For this particular function, we have r of t equals 2ti minus 3 plus tj for this particular example, okay? So how could I go about plotting this? We aren't super familiar with vector value functions, with what they would look like. This one, if you think about it, you might actually be able to get it. This is a familiar form. Generally, we can always try plotting a vector valued function by just plugging in points. For example, I could plug in 0. I get the point 0, -3. I could plug in 1. I get the point 2, -4. Right? And I could keep on doing that until I have enough points to generate a picture. I could plot all these points. Okay? And that works. And a lot of times that's the only option available. But a lot of times for these two-dimensional vector valued functions, we have another option available to us. We can do something called eliminate the parameter. So let me show you what I mean. So this guy here, this 2t, that's going to be the x value for any value of t that I plug in, right? So the x will always be 2t for any xy point that this vector valued function outputs. Similarly, the y value that this vector value function outputs for any value of t, I'm going to get -3 plus t. Okay? Or if you prefer, if you distribute that negative, -3 minus t. Now, what I can do is I can isolate the t in one of these equations and then substitute the resulting equation into the other to eliminate the t entirely. And I could get a more familiar equation in just y and x. Okay, so let's take this one. Let's isolate the t, divide both sides by 2. T is x over 2, and I could plug that in here. So if I plug that in, I get y equals -3 minus the t, which is x over 2. And if I write just a little differently, I get y equals -1 over 2x minus 3. These describe the same curve, but this is much more familiar, right? This is a line. Let's graph the line real quick. It has y-intercept at 0, -3, and slope -1/2. So down 1 over 2. Okay, and that's what the equation of the line looks like. That's the graph of the line. That's what this vector value function will generate. And I was able to do that a lot easier by using this form, where the parameter t was eliminated from the set of equations. Okay. Now, I should emphasize that this isn't perfect. By using this, we actually lose some information. That parameter t describes motion, right? It's not just a static line. It describes motion. It tells us which direction we're going in and how fast, if we think about it as a time variable. And just like how you can't take a picture of a static car and know all the details about its path, you don't know how fast it's going, whether it's going forward or backward or moving at all. Is it going slow? Is it going fast? 5 miles down the road, does it speed up? Does it slow down? You can't get any of that from a static image, right? Just like you can't really tell the details of the trajectory from this without that parameter variable that we think about as time. okay? Nor can we communicate all of that in this graph anyway, right? I can't communicate that in a static graph. I need some kind of animated graph, and I can't do that on a static piece of paper. But I can at least indicate the orientation of the curve. Is it going to the right downhill, or are we going to the left uphill? This is information we want to know, okay? That information isn't found here. We know what the curve looks like that we trace out, but which direction is the path going? Okay, what's the trajectory? In this case, I've already plotted it. I already have a couple points here. What we want to do is we want to use what we have here, use the information here, and at least describe the direction of motion, right? So when t is 0, I get 0, -3. That's this point here. And when t equals 1, I get 2, -4. There happens to be the 2 points I already have plotted. But this point here was when t equals 0, and this point here was t equals 1. So as t is increasing, I'm going this direction. And so I draw a couple of arrows to indicate the trajectory of the vector valued function, the orientation of the vector valued function. Okay, let's do another one that's just a little trickier. Okay, we want to express the vector valued function r of t equals 1 over t ij in Cartesian coordinates. So same thing. We're going to first break this into what this means for the x. So x is 1 over t, and the y. For each point, the y will also be 1 over t. In this case, I can right away say that y equals x. That's an easy line to draw. But as we'll see, the behavior of the trajectory is going to be really strange. Okay, and I'm draw these arrows out of habit, but I don't want to draw them since I want to emphasize the orientation. I don't want to confuse us with multiple arrows. Okay, so that's the curve. That's the line that this vector valued function describes and summarized by this equation where we have eliminated parameter t. Okay, but what we want to do is we want to describe the orientation. Which direction are we going? Okay, first off, notice I can't plug in t equals 0, right? But as my t's get bigger, my fraction gets smaller. My x and y values get smaller, right? Larger t's, smaller fractions. So that means the x and y components of points are getting smaller, which means I must be going this way, right? But notice there's a limit. I kind of slow down. I can't quite get past this point because if t's are just getting bigger, if I'm plugging in positive values of t, then x and y are just going to be positive, right? Well, what happens if I plug in negative values of t? I get pretty much the same thing happening, but I'm getting negatives, right? So if I have a big negative number for t, then I have small negative fractions, right? Big number, small fraction. So that means something close to 0. As t's get bigger, I'm getting close to 0. But, so I'm going that direction. If t's are small and negative, then the fractions will be big and negative. Small denominator, big fraction. Okay? So small, I start up here, and then I go this way. And I'm slowing down as I approach here. Okay? So I have almost 2 different trajectories of t, and because t can't be 0, they never cross, right? When t is positive, I'm going that way. Start fast, and then slow down. When t is negative, small negative numbers, I go this way. When it's fast, or when the t is small, I go fast. And as they get bigger, I slow down. And they never actually quite reach the center, right? There's no t I could plug in that will give me that center value. This is an especially strange example, but I just wanted to show you that trajectories aren't always going, one direction. They're not always going to be going this way or this way. In this case, we have almost two separate trajectories described by the same vector valued function converging onto the origin. Okay? All right, let's look at one more example. Here we have the vector valued function r of t equals 2 sine of t, comma, negative 3 cosine of t. Now, just as before, we want to eliminate the parameter if we can. So x is equal to 2 sine of t. Y is equal to negative 3 cosine of t. But in this case, there's not an obvious way to isolate the t. In the previous two, in this one, we were able to isolate the t in one of the equations and then plug it into the other equation. In our second example, it just so happened that both of the x and y were equal to the same value, so I was able to set them equal to each other right away. But in this example, I can't easily isolate the t because, remember, arc sine and arc cosine, they're not true inverse functions. And so I'd be losing some information by taking the arc sine or taking the arc cosine. What's more, these just aren't equal to each other, and there's no obvious way to get them equal to each other, right? So what can I do here? Well, whenever you have sine and cosine as involved in the x and y, one important and useful property to remember is the Pythagorean identity. Always remember that cosine squared plus sine squared equals 1. Okay? So if I isolate cosine and sine in both of these equations, so in this case, x over 2 is equal to sine of t, negative y over 3 is equal to cosine of t, I could plug these into this formula. Okay, so cosine squared of t, cosine of t is negative y over 3. So I get negative y over 3 squared plus sine squared of t. Sine of t is x over 2. So x over 2 squared equals 1. So I get y squared over 9 plus x squared over 4 equals 1. And hey, that does look familiar. That's an ellipse. It's an ellipse centered at the origin. So I'm going to go 3 units out in the y direction, up and down. And from the origin, I'm going to go 2 units out in the x direction, left and right. And I'm just going to draw the ellipse that goes through all 4 points. There's my ellipse. The only thing left to do now is draw arrows to describe the orientation. Am I going to be going clockwise or counterclockwise? And again, for that, I can't use this because I've dropped all information about what points I reach when, right? I need to go back here to the original vector valued function, and that will tell me which direction I'm going, because I can plug in a few points and see, okay, at certain values, what am I getting here? Okay, so what I'm going to do is I'm going to plug in easy values. And I just need a couple. to figure out the general direction, right? So 0 looks easy. If I plug in 0, sine of 0 is 1. So 2 times 1 is 2 in that first component. And then cosine of 0, I'm sorry, other way around. Sine of 0 is 0. Cosine of 0 is 1 times negative 3 is negative 3. Okay, so my first point is this one right here. This one right here is the point at t equals 0. Okay, now I could plug in t equals 1, but sine of 1 and cosine of 1 are not easy to evaluate. So I'm going to plug in a t that I know I can easily evaluate. How about pi over 2? I can easily calculate sine of pi over 2. I can easily calculate cosine of pi over 2. So if I plug in pi over 2, sine of pi over 2 is 1 times the 2 that's already there is 2. Cosine of pi over 2 is 0 times the negative 3 is 0. Okay, so 2, 0, that's this one, that point right here. T equals pi over 2. So as the t is increasing, I'm going this way. And that's going to be the direction I keep going. You can plug in more points if you want to be sure. But that's the direction of increasing t. The orientation of this particular curve is counterclockwise. Next, I want to look at some examples where we need to construct vector-valued functions that meet certain criteria. We're going to need to construct vector-valued functions every once in a while, so it's helpful to have this skill down. Okay? For this one, we want to find a vector-valued function that traces the line from one point in three-dimensional space to another point in three-dimensional space. Now, this is actually something we already know how to do. We already know how to find a parametric equation of a line. Remember that we can write the parametric equation of a line as some initial point on the line, plus my parameter t times a direction vector, a vector parallel to the line. This is a vector-valued function. I take in a single value t, and the output, once I combine all this, is a vector. Okay, so we know what we need to do. This is the same thing that we've done in previous sections. So we need a point on the line, and we need a vector parallel to the line, a direction vector. The point on the line is easy. I've got a couple to choose from already. Okay, direction vectors are just a little trickier. So we need to point from one point to another point. Now we know how to do that. The only thing we need to be really careful of here is that we get the direction correct. We want a vector valued function that traces a line from point P to point Q. The orientation of our vector valued function matters. Okay, so we want to make sure we go from point P to point Q and not the other way around. Okay. So in this case, that means v, we know how to find a vector that points from one point to another. That's n minus start. Okay. I want this vector to end up at Q. So 0, 1, 0. And it starts at P, 1, 0, 1. And if I do the subtraction, I get negative 1, 1, negative 1. Okay, that direction vector is the vector that points from P to Q. That'll make sure my vector valued function is pointing in the correct direction. So let's plug in. I could plug in a point. I've got some options here. Really, when you're finding a vector valued function, a lot of times you have a lot of options. Because as we've talked about, you can go, you could trace the curve in one direction, you could trace the curve in the other direction, you can go slow, you could go fast. Okay, in this case, it's what point do we start from? I'll start from point P. Okay, just be aware that there is, based on these instructions, there's more than one possible correct answer here. Okay, so technically that's my answer. Though if I want to do the scalar multiplication and vector addition, I could write my answer as 1 minus t, 1 minus t. That is a vector valued function that traces out the line that goes from point P to point Q. Okay, we make sure we have the orientation correct because we made sure that our direction vector is pointing in the direction from point P to point Q. Okay, let's look at another one. This one's just a little different. We want to find a vector valued function that traces the parabola y equals x squared from left to right. Okay, so this isn't just a line, but for a problem like this, it's pretty straightforward. If you have a relationship between y and x like this, you can often just assign one variable to be equal to t. So I'm going to set my x equal to my t. Okay, and then since y is equal to x squared, my y could be t squared. I'm setting x equal to t. And then my y is equal to x squared, but I just said x equal to t, so y is equal to t squared. So that's my y component. Okay? So that will trace out the parabola. The only thing left to check is, will it trace it out from left to right? The best way to do this often is to plug in a few points. So we know what this looks like. It's a parabola. Okay, but let's plug in a few points for our parameterization. Make sure our orientation is correct. Make sure we're going from left to right. And often just a couple points is all you need, a couple values of t. So I'm going to plug in t equals 0 and t equals 1. If you're unsure, you can plug in more. Okay, so t equals 0, I get r of 0 is 0, 0. I get the point 0, 0. Okay, and if I plug in 1, I get 1, 1. 1, 1, right around there. Okay, and so this is at t equals 0, this is at t equals 1, and so I am going from left to right, aren't I? And so the orientation is correct, which means this is my final answer. I don't need to adjust anything to reverse the orientation. I'm already going left to right like I want to. Okay? All right, great. Let's do one more. This one's just a little trickier. We want to find a vector valued function that traces the ellipse 4x squared plus 9y squared equals 36 in the clockwise direction. Okay? So the best way to deal with orientation is to worry about that at the end. That's our very last thing to worry about. It's actually easy to correct if we have the wrong orientation. So I'm just going to start off by finding a vector value function that traces the ellipse. So 4x squared plus 9y squared equals 36. Now I can't use the same trick here that I used in the last problem. I can't just set x equal to t and then set y equal to whatever it is with the x, right? Because if I do that, if I isolate the y here, so 9y squared, let me do it actually a little over here to the side. 9y squared equals 36 minus 4x squared, divide by the 9. Y squared equals 36 divided by 9 is 4 minus 4 9's x squared. Okay, take the square root. I don't get just one value for the y. I get two, a plus and a minus. Taking square roots are dangerous like that. So I can't just set x equal to t and then plug that in for the x here because I won't have one specific value of y. What this means in effect is I'll either only have the y's positive or only have the y's negative. So I'll have to pick one, which means I'll only get the top half of the ellipse where the y's are positive, or I'll only get the bottom half of the ellipse where the y's are negative. and that's not what I want, right? So you got to be careful with using an approach like this, especially if there's squares lying around. You can't just take a square root because you end up splitting the graph, okay, into a positive and a negative. Okay, so I can't do that. What can I do? Well, first off, first thing that's bugging me about this, this ellipse isn't in standard form. So let's put this thing in standard form. Let's divide both sides by 36. That'll get me a 1 over here on the right-hand side, which is what I would expect if I wanted the equation of an ellipse in standard form. I'm going to divide everything by 36. Okay. And fortunately, everything goes in nicely. 4 goes into 36 9 times. 9 goes into 36 4 times. And 36 goes into 36 once. Okay, beautiful. So now this is in standard form. Okay, and now I have something squared plus something squared equals 1. Now that rings bells. If you're a mathematician, that rings bells. We know that if we take cosine squared plus sine squared, we get 1. Okay, that's the Pythagorean identity, one of the most important identities in trigonometry. This is what I kind of want to aim for. I want to choose the parameterization for x and y so that this equation and this equation are the same equation. Okay, so in order to do that, I need this x squared over 9 to be cosine squared. Okay, so that means x squared over 9 equals cosine squared. And I need y squared over 4 to be sine squared. Okay, as long as that holds, I'm good. So I'm going to take the square root of both sides. X over 3 equals cosine of t. Y over 2 equals sine of t. Okay, notice I didn't have to worry about the plus or minus. Really, x could be equal to plus cosine or minus cosine. Sine could be equal to, or y over 2 could be plus sine or minus sine. But as long as this property holds, then I will have this. So I get to choose in this case whether I want the positive or negative, in other words. Okay, because whether x over 3 is equal to positive cosine or negative cosine, when I square it, cosine squared of t will be x squared over 9, as long as whatever sign I have here is equal to x over 3. So since I get to choose, I'm going to choose the easier one. I'm going to choose positive. Okay? So this is my choice for x and y. That makes this happen, which makes this happen, so I'm guaranteed to get an ellipse. Okay? Let's just isolate the x and the y. So I get x equals 3 cosine of t. I get y equals 2 sine of t. And that's my parameterization. I'm done. R of t equals 3 cosine of t, comma, and then y equals 2 sine of t. Okay? That is a parameterization that will trace out an ellipse. Now we have one thing to check before we're done. We do have a particular orientation that we want. We want to make sure we go in the clockwise direction. So now that we have a vector valued function that traces out the ellipse, let us check the orientation, and if needed, we can make an adjustment. Okay? All right. So I'm going to draw the picture just so we have something visual to work with. Okay, we know this ellipse is x squared over 9 plus y squared over 4 equals 1. We know how to graph that. In the x direction, I move 3. From the center, in the y, I move 2. Okay, so there's my ellipse, and I need to determine if I'm going clockwise or counterclockwise. Okay, so let's plug in a few values of t and see if this parameterization of the ellipse is going to have the orientation I want. So t, r of t. And again, just the couple's usually fine. So I'm going to plug in 0. If I plug in 0, r of 0, I get 3 times cosine of 0. Cosine of 0 is 1, so I just get 3 here. And 2 times sine of 0. Sine of 0 is 0. And 2 times 0 is 0. So I get the point 3, 0. I get this point right here. T equals 0. And then one more. And I want to plug in a t that's going to make this easy to evaluate. So I'm going to plug in pi over 2. If I plug in pi over 2, cosine of pi over 2 is 0. So that first component is 0. Sine of pi over 2 is 1. So that second component is 2 times 1, or 2. I get this guy up here. T equals pi over 2. Okay, so as t increases, I'm going this way. This is the orientation of my current parameterization. I'm going counterclockwise. That's not the direction I want. The orientation is counterclockwise. Okay, so how do I change the orientation? There's an easy trick for this. All you want to do is you want to take all those t's and you want to flip them around. Okay? To do that, all you do is you take every t in your parameterization and you just make it negative. Okay? R of t equals, so this will become 3 cosine negative t. Comma 2 sine negative t. This will go in the opposite direction because now, if I plug in 0, I still get this point. But now, in order for what is in cosine to be pi over 2, I would have to plug in negative pi over 2 to the t, right? That way the double negative becomes positive. So now it's negative pi over 2 in this adjusted parameterization that will give me this point. Okay, negative pi over 2 is less than 0. If I have negative pi over 2, then I'd be going this direction. I'd be going the direction I want, clockwise. Okay, and that's not just a quirk for this particular problem. That always works. If you find your parameterization has exactly the wrong orientation, just change all your t's to negatives. Okay, just throw a negative in front of every single t, and it will flip the orientation to exactly the opposite. Okay? And so that is our final answer there. We now have a parameterization for the ellipse that is going clockwise. Okay, and if you really wanted to, you could tidy this up. There's some nice rules with having a negative inside a cosine or a sine. For cosine, the negative actually doesn't make a difference. Okay, cosine stays the same. Okay, for sine, if you have a negative inside sine, it actually comes out. Negative 2 sine of t. So if you wanted to tidy up a little bit, that would be a final answer. Okay, equivalent to this one. Now let's look at similar examples in 3 dimensions. So for this first one, we want to find a vector equation that represents the curve of intersection between a paraboloid, z equals 2x squared plus y squared, and the surface x equals e to the y. And it's given us a little hint. We want to write the equations so that the y of t component equals t. The y of t component here is the middle component, right? we're thinking of this, our vector valued function is having three components. Y of t is the function in the middle, the y component, okay? So this, we already know that that should be t. Okay, let's get an idea of what we're working with here. Let's pull over a graph. So there's our paraboloid, z equals 2x squared plus y squared. We want to look at the intersection of this paraboloid with the surface x equals e to the y. Okay? And so the intersection we get is this shape right here. So we want to be able to describe this shape in 3 dimensions. Okay? We want to describe this path in 3 dimensions. So how do we do that? Well, we approach this very similar to how we approach some of the 2D problems. We know that y of t equals t. That's a given, okay? And it really is the best choice, by the way, for finding parameterization. It's the easiest choice because immediately I get a very easy way to express x. If y equals t and x equals e to the y, then I could plug this into that, and I get x equals e to the t. And now I have an x and a y, right? And what's more, I know what z is in terms of x and y. Z is equal to 2x squared plus y squared. So if I plug both of these in here, then x is e to the t, so that's e to the t squared, plus y is t squared. Just tidy up a bit, 2e to the 2t plus t squared. I have an x, a y, and a z. I have my parameterization. Okay, that easy. So let's see, x is e to the t, y is t, and z is 2e to the 2t plus t squared. That vector valued function describes this curve here in 3-dimensional space, the intersection of the paraboloid and the surface x equals e to the y. Okay? All right, let's do another one. This one's a little trickier. This one we want to find the vector equation that represents the curve of intersection of the cylinder x squared plus y squared equals 16 and the surface z equals x plus 2y. Okay, so let's get an idea of what that looks like. So x squared plus y squared equals 16, that's a cylinder, right? If we just look at the xy plane, of course, it's a circle, but we stretch it in the z direction, we get a cylinder. And z equals x plus 2y, that's going to be a plane. And so we want the intersection of the cylinder and the plane. And we get this kind of elliptical shape. Okay? So we want a vector valued function that can describe us traversing this curve. Okay. Well, it gives me a hint here. X of t equals 4 cosine t. So we're going to assume that. Okay, so x equals 4 cosine of t. Now we need to know more about y. Well, I know z is equal to x plus 2y. So if I can find a good choices for x and y, I could plug that in and immediately find z, right? So z is going to be easy if I can find y. So looking at this other condition, I know x squared plus y squared equals 16. And so I need a choice for x and y that's going to make this work. And here we can see that this really is a great choice for x. X equals 4 cosine t. Because I look at this and I say, how do I describe the equation of a circle? Well, I traverse the unit circle, I traverse it with sine and cosine, right? Same thing here, okay? I want, if I divide by 16 to kind of turn this into 1 on this side, okay? So I get x squared over 16 plus y squared over 16 equals 1. Or if I think about it, x over 4 squared plus y over 4 squared equals 1. I could say, okay, if I think of this as cosine and I think of this as sine, then I'd have cosine squared plus sine squared equals 1, right? Whenever I want to parameterize something that's 2 squared things equals 1, cosine squared plus sine squared. That's what I should be thinking. It's the easiest way to parameterize something like this. So we could choose x over 4 to be cosine. That way it'll match this, right? Once I move that 4 over. And y over 4 to be sine. And that way x over 4 is cosine, so this is really cosine squared. And if I choose y over 4 to be sine, this will be really y squared. And I know cosine squared plus y squared equals 1. Okay, so that choice works, which means x equals 4 cosine of t, y equals 4 sine of t. Okay, with just this choice of x and y, this gives me a circle of radius 4 in two-dimensional space. Of course, we're in three-dimensional space, so we'll have to take that into account in a moment. But in two-dimensional space, just this choice of x and y, we get a circle of radius 4. Okay, we see this type of thing a lot. If we use cosine and sine, we get a circle. If we throw the same coefficient in front, we get a circle of that radius. Okay, all right, we got x and y. Let's just plug into this third equation, or this other equation now, z equals x plus 2y. And we will have our z component also. Z equals x plus 2y, plug in. I get z equals 4 cosine t plus 2 times 4 sine of t. And just tidy up a bit. I get 4 cosine t plus 8 sine of t. So my final answer, if I put x, y, and z together, r of t equals, my x function is 4 cosine t. My y function is 4 sine t. And my z function is 4 cosine t plus 8 sine t. That parameterization will traverse this curve in three-dimensional space. Okay? All right, one more. Here we want to find a parameterization for a circle of radius 3 with center 3, 2, negative 2 in a plane parallel to the xy plane. Write your parameterization so the x component includes a positive cosine and the y component includes a positive sine. Okay, so let's first draw a little picture of what we're dealing with here. So x, y, z. We want a circle of radius 3 with this center 3, 2, negative 2. So 3, 2, negative 2. Three, 2, negative 2, something like that. Okay. So there's our center of our circle. We want this circle to live in a plane parallel to the xy plane. So the xy plane is this one here, right? We want to be parallel to that. So our circle is going to be parallel to that xy plane. It's three on the okay. So something kind of like that. It's not a perfect drawing, but the radius we want to be 3. Okay. All right. It's going to be easiest to kind of think about this in pieces. First off, notice that this curve only lives in this plane. The z value will never, ever, ever change. So if we're looking for the x, y, and z components, the z value has to be -2 in this case. We're parallel to the xy plane, so the z never changes. We just go around a circle, locked in this one plane. Okay? Now, in x and y, we do change. We go around in a circle. And if we just kind of looked down from above, then we'd see this circle and just look like a two-dimensional circle in the xy plane. So in the xy plane, the x was 3, 2, 3. The y was 2. So looking down from above, the z-axis is pointing right at your face. Okay? Here's x. Here's y. And we have a radius of 3. Don't want it dotted. So something like that. Okay? How do I describe that circle? So this is the picture from above. Okay, looking down the z-axis. How do I describe that circle? Okay, well, we know cosines and sines are great for describing circles. We know we want x squared, but well, I shouldn't say that. Okay, a circle of radius 3, we would have x equals 3 cosine of t, and y equals 3 sine of t. We've seen that, right? Hopefully we've seen it enough times that I don't need to rederive it again. So this gives a circle of radius 3, but it's at the origin. Okay, we just need to offset it a little bit so that we have this center specifically for x and y. Again, we don't really have to worry about the z. It's just constant. We've got z covered. Okay, we're just figuring out what's happening with the x's and y's. Okay, so to offset it, the trick here, the center would normally be 0, right? So I just want to take this 0, this center here, I just want to move it over. Okay? So that means I want to move 3 units in the x direction so I can get to that center. Okay? 3 units in this direction, and then 2 units in the y direction. The y would be 3 sine t plus 2. So I'm just using our new center to offset the circle. Okay, and that's our x and y components. So let's take those, let's plug them in up here. 3 make sure I have enough room, 3 cosine of t plus 3, 2 sine of t, I'm sorry, 3 sine of t, 3 sine of t plus 2. The 3 cosine t, 3 sine of t give us a circle of radius 3. By adding 3 to the x, by adding 2 to the y, it shifts the x and y coordinates of the center to 3, 2. And then I just shift it down to the plane z equals -2. Okay? That's going to be our answer. Let's throw it in the calculator. Make sure that it actually looks good. Okay? So we will have 3 cosine of t plus 3, comma 3 sine of t plus 2, comma -2. From 0 to 2 pi. We want to make sure we get the whole circle there and make it a little brighter. Okay. So there's the positive x-axis, positive y-axis, and down here is z equals -2. We have that circle. Okay, if we look from above, we get the circle we want. Let me hide the xy plane. It's kind of getting in the way. We have the circle we want, right? It's just shifted down, z equals -2 units. So it does give us what we want here. Finish off this section, we're going to talk about limits for vector valued functions. What do we mean when we want to take the limit as t approaches some value for our vector valued function? Okay. Now I could get into details of definitions and such like that. Honestly, it's more important that you understand the intuition behind this. The limits for vector valued functions, the intuition we get is the same as the intuition we have for single variable functions. That is, the limit is the value we get close to, right? The limit is t approaches a of, let's say the limit is x approaches a of some function f of x equals L if, as x gets closer to a, f of x gets closer to L, right? That's the intuition behind it. It's the same thing here. For vector valued function, the limit as t approaches a is equal to some vector v, if as t gets close to a, the output vector gets closer to vector v. Okay? And it's important to understand that that's only going to happen if each component gets closer. Okay? If we're getting close to this and say we get close to v1, v2, v3, maybe that's our limiting vector. Okay? Well, that limit only exists if the first component gets close to v1 as t gets close to a, right? It only exists if also the second component gets close to v2 as t approaches a. And the third component gets close to v3 as t approaches a. Which means that this limit only exists if the limit of each individual component exists. So that's how we find the limit generally of a vector valued function. Let's write it formally. Okay? Given a vector valued function, R, which takes some scalar, our parameter, which is a real number, and takes it to some n-dimensional space, the limit as t approaches a of r of t exists if and only if the limit for each component of r of t exists. In that case, the limit as t approaches a of r of t is just equal to the limit of the individual components. Okay, so rather than some big new math, we're just doing the same thing we've always done. We just need to take the limit for each individual component. If any one of those components does not have a limit, then the entire vector valued function doesn't have a limit as t approaches that value. Okay. Now we're going to focus mostly on limits, but the same holds true for continuity. Our intuition with continuity is the same. Our intuition is, hey, it's continuous if you could draw the picture without lifting your pencil, right? This is continuous. This would not be continuous. I had to lift my pencil in that one, right? The same thing for vector valued functions. If you can traverse the curve without any gaps or breaks, it's continuous. And it will only be continuous if each individual component is continuous. Let's take a look at an example. Here we want to evaluate the limit as t approaches 0 from the right of the vector valued function with sine of 3t over t as the first component, natural log of t as the second component, and 4 as the third component. Okay? So the limit will only exist if the limit for each component exists. So the limit as t approaches 0 from the right of sine of 3t over t, comma, natural log of t, comma, 4 would be equal to, if it exists, the limit as t approaches 0 from the right of just the first component, the limit as t approaches 0 from the right of just the second component, and the limit of as t approaches from the right, t approaches 0 from the right of just the third component. Okay, the limit exists. It's equal to the vector with the limits of each component. If any one of these components does not have the limit, okay, or if it's infinity or negative infinity, the limit for the vector valued function does not exist. All right. So let's start with the easy one. For this one, limit as t approaches 0 from the right of 4. Well, 4 is 4 is 4. It never changes. So as t changes, that 4 just stays 4. So we are approaching 4. That one's easy. Okay. This one we may have to think about a little bit. This is a limit that we would have learned in Calculus 1. It's been a while, right? The key here is to recall that the limit as t approaches 0 of sine of t over t is equal to 1. Okay? And that's not quite what we have here. So we need to adjust it to kind of fit this framework. Okay, but this is one that we learned in Calculus 1 we should have memorized. But we need to adjust it, all right? T approaches 0 from the right. Well, as t gets close to 0, I mean 3t gets close to 0 and t gets close to 0, but they're not approaching at the same speed. And that's what we need. Okay, we need what's inside the sign in the numerator and what's in the denominator to get to approach 0 at the same speed. If we could get that to happen, then the limit equals 1. Okay? What would be easier, or rather, what we want to do here is get the same pattern here. Okay? Now, there's no way, no easy way to get this 3 out of the sine function. Okay? What would be easier is to get a 3 down here. That way, these will approach 0 at the same rate. Okay? So what I'm going to do is I'm going to multiply top and bottom of this fraction by 3. That gives me the limit as t approaches 0 from the right. This 3 I'm just going to stick out in front. 3 sine of 3t over 3t. Okay? Now this is what I want. Okay? Because if t is approaching 0, 3t is also approaching 0. Now what's inside the sine is also approaching 0 at the same speed as what's in the denominator is approaching 0. And so we have what we want here. Okay? We have this same sort of pattern. And so what that means, let's see, we could drop the limit now. We're going to take the limit. We get the 3 in front. And then this limit, as t approaches 0, since what's inside the sine and what's in the denominator are approaching 0 at the same speed, we're going to get 1. And so the limit is 3. So we got that limit. Brilliant. Okay, so that's 2 down, 1 to go. Let's try this one. We need the limit as t approaches 0 from the right of natural log of t. Now for this one, there's no real tricks we need to know here. We just need to know what the graph of natural log of t looks like. Okay? Graph of natural log of t has an asymptote on the y-axis. It looks kind of like this. Okay? We're interested in the limit as t gets closer to 0 from the right side. So the right side's over here, and we want to get closer to 0. So as I get closer and closer to 0, what's the output value, the y value getting closer to? Well, I never can quite reach 0, right? And this just keeps on going down and down and down and down and down. Closer and closer and closer to that asymptote, but never quite reaches it. Okay? This limit is negative infinity. All right? Technically, negative infinity means the limit does not exist. We usually write negative infinity because we want to describe that behavior. But negative infinity isn't a number, it's an idea. This limit technically does not exist. Just a special kind of does not exist. Okay? What does that mean for the limit as a whole? We had 2 components where the limit exists, and 1 component where the limit does not exist. But in order for the full limit of the vector valued function to exist, it needs to exist for all 3 of the components. Because 1 component fails, for 1 component the limit does not exist, the whole limit does not exist.